Salam and welcome everyone. So today we're going to be working on the question on your screen that says calculate the final temperature, the work done, and the change in internal energy when 1.0 mole of NH3 gas at 298 Kelvin is used in a reversible adiabatic expansion from 0.50 dm cube to 2.0 dm cube. So the first thing you have to note is this. While they've told us what they want us to solve for, which is basically for us to determine the final temperature, the work done, so the adiabatic work done, as well as the change in internal energy for the adiabatic process, we're told that 1 mole of NH3 gas, so that is the number of moles, so it's 1.00 mole and of NH3 gas at 298 Kelvin. So they've also told us the temperature that we're supposed to work with, which is 298 Kelvin. And we're told that this is a reversible adiabatic expansion process. It's important for you to know that whenever you're given a chemistry question and you have things like adiabatic, reversible, expansion, or in this case, it's just an adiabatic question, you have to start thinking of formulas and what the adiabatic expansion process entails. So that means you're not gonna do use an isothermal formula for an adiabatic question. Do you understand what I'm saying? So the keyword is adiabatic expansion, meaning there's an increase in volume. And then, of course, a reversible adiabatic expansion is what the question asks. So now we know we're dealing with an adiabatic problem. Then we're told that we have an initial volume of 0.50 dm cube. And of course, because an expansion, there's an increase in volume. So our final volume, according to the question, is 2.00 dm cube. So what we're supposed to find is the final temperature, the work done on the adiabatic process, as well as the change in internal energy. So the first thing you have to note is for you to write the formula that works in determining the final temperature of an adiabatic process. So the formula is simply the V initial, okay, times the T initial raised to the power of C is equal to V final times T final raised to the power of C. So the raised to the power of C is just applying to the temperature. And you may be wondering, okay, this is a good question. Why? Because we have the T initial. We have the V initial. We actually have the T initial here, which is just 298 Kelvin. I apologize. I forgot to write T initial here. So we have the V initial, we have the T initial, we have the V final, but we are asked to find the T final. But then we have an issue here because we've also been given the formula comes with a parameter C. So what is C? We're not given C in the question. So what that teaches us is that our understanding of the concept is what we're going to use to determine C. So using our knowledge of physical chemistry based on the physical chemistry Atkins textbook, we're told that C is actually equal to the molar heat capacity at constant volume divided by R, which is a gas constant. So the molar heat capacity at constant volume for the gas, so for NH3 gas, is what CV comma N stands for, as well as R is just the gas constant, which is basically a constant. So the CV comma M is going to vary from gas to gas or from molecule to molecule. In this case, we're dealing with an NH3 gas molecule. So what we have to do is to determine what CV comma M is, and because we're dealing with physical chemistry, all of this information is already like a fact or a fixed value. So what I'm trying to say is that a gas constant, we know 8.3145. CV comma M for NH3 is also an exact constant value. So looking at our book, the resource section of the Atkins Physical Chemistry textbook, at the back of the book, I determined CP, okay, comma M to simply be 35.06 joule per mole Kelvin. So this is what I have. Now you may be wondering, okay, why are you dealing with CP comma M? We're actually supposed to be dealing with CV comma M. So how come we have a CV comma M? It's very, very simple. The reason is because when you have your CP comma M and you have your gas constant, you can determine what CV comma M is. So CP, okay, comma M minus CV comma M is equal to the R value. We know the CP comma M, we know the gas constant 8.3145. So that means we can determine CV comma M. So CV comma M is going to equal CP comma M minus R. CV comma M then becomes CP comma M is just 35.06 joule per mole Kelvin minus gas constant, which is R, as which is just 8.3145 joule per mole Kelvin. So yeah, so CV comma M is just going to simply be subtracting this, and we end up with 26.7455 joule per mole Kelvin. So this is basically the answer to this. So we have CV comma M. Well, our work is still not done because we're supposed to determine the value for C. Well, since we know C is what we're looking for, and we know CV comma M is just simply what we determine at the bottom, which is 26.7455. So that would be 26.7455, okay, joule per mole Kelvin divided by the value of R, which is just 8.3145 joule per mole Kelvin. So cancel out the joule per mole Kelvin, cancel everything out because C actually doesn't have a unit. So when we divide this by putting it in our calculator, we end up getting 3.2167. So this is the value that we are looking for, and we've determined C to be that value. So now that we know the value of C, we're gonna continue solving our question. So rewriting this, and I'm gonna rewrite what we have. I have V initial, okay, divided by T initial raised to the power of C is equal to V final, T final raised to the power of C. So yeah, and T final is what we're supposed to determine, right? Because that's what they asked us to do. So T final becomes V initial divided by V final times T initial raised to the power of C. But we know math, we can, the issue here is if we substitute 3.2167 into every single thing, it's going to make our work cumbersome and it can even make our work confusing. So we have to apply our knowledge of power as well as our knowledge of mathematics, and we have to raise all of the left side of the equation and the right side of the equation by 1 over C. By 1 over C. So what this means is just simply we end up having TC, okay, times 1 over C is equal to V initial divided by V final raised to the power of 1 over C, okay, times T initial, okay, raised to the power of C times 1 over C. Very simple. We can just simply cancel out the C's here, cancel out the C here. So rewriting our equation, the new found equation that that is going to be easy for us to work with would be T final is going to equal V initial divided by V final raised to the power of 1 over C times T initial. So this is actually the equation that we're going to be working with in this question. So let me rewrite this here and we can now simply substitute. So T final would be our V initial. Going back up, we see that V initial is 0.50 dm cube and our T final is 2.00 dm cube. So V initial is just 0.50 dm cube divided by T final. V final, sorry, V initial 0.50 dm cube, and then V final is 2.00 dm cube, okay, raised to the power of 1 over C. We now have C value to be 3.2167. So raised to the power of 3.2167, okay, times T initial. Going back up, what is that? T initial, we see our T initial to simply be 298 Kelvin. So times 298 Kelvin. So you cancel out the dm cube, cancel out the dm cube. Yeah, we cancel out dm cube, cancel out dm cube. We have the T final is just simply 0.5 divided by 2.0, which is just 0.25. Okay, raised to the power of 1 divided by 3.2167. When you input this information in calculator, you end up with 0.3109. I'm just purposely like making it easier on you guys so you can know how all this calculation is going on. So basically, I'm going to resubstitute all of this information to the decimal, right, and the fraction. So this is going to be raised to the power of 0.3109. So I just did the fraction division to get a decimal, and I'm just going to raise that to the power of the what we just calculated times 298 Kelvin. So of course, T final is just simply 193.658 Kelvin. Now, of course, the next thing we have to simply do is for us to um do what we do in chemistry or science, which is just to approximate to the proper number of significant figures. If you look at our work, everything we've been given in terms of numerical value is in 3 significant figures. So here 1.0 is in 3 sig figs, 298 is in 3 sig figs. This one right here is in 2 sig figs, this one is in 3 sig figs. But the initial temperature was given to us in 3 sig figs. So I'm just gonna put our final answer in 3 sig figs. So our T final is approximately 194 So our T final is going to be approximately 194 Kelvin. So this is basically the answer to this question. Now, or the first part of the question, right? T final. Now we're asked to determine the adiabatic work done. So the adiabatic work done is what we're asked to determine. Well, this is not hard. We have to just note that the adiabatic work done formula for this is just the number of moles times CV, comma M. So the molar heat capacity um, at constant volume times the change in temperature. This is basically the formula that we're going to use to determine it. I want to quickly say something. The only reason why we have N times number of moles times the molar heat capacity is because we have our work in molar heat capacity. If here's a question where we're just giving heat capacity, which is just CVM, CV comma M is molar heat capacity, CVM is just heat capacity. We're not gonna multiply by number of moles because we don't need to. We're multiplying by number of moles here because we have a molar heat capacity and we want the moles to cancel out so that our final answer is going to just simply be joules. You understand, right? Because for work done, our final answer has to be in joules. So work done is just the number of moles in this question going back up is 1.0 mole. So that would be 1.00 mole times the molar heat capacity at constant volume. We've determined that to be 26.7455, 26.7455 joule per mole Kelvin times changing temperature, which is just T final, okay, minus T initial. So changing temperature is just simply 193.658 Kelvin. So that would be 193.658 Kelvin minus change T initial, which is just what do you call it? What's T initial again? 298 Kelvin. And now you may be wondering, why didn't I just say 194? It's because in science, chemistry, whatever you want to call it, it's better for you to use the raw values rather than just using the approximate values if you're still calculating. It's when you're completely answer the question that is best for you to approximate. But if you're still going to use the same if you're still going to use the same parameter to calculate, it's better for you to use as much of the raw value as possible, but please do not approximate to the proper number of significant figures until the end. So it's better for me to use the raw value to get a more accurate answer than for me to use the approximated value already. So yeah, that's just science knowledge. So 1.0, so cancel the moles. Yeah, that would be that. So 1.00 times 26.7455. So that's just 26.7455 joule per Kelvin times 193.658 Kelvin minus 298 Kelvin is just simply minus 104.342 Kelvin. So cancel out the Kelvin, cancel out the Kelvin. So work done would just be 26.7455 joules times negative 104.342. That's simply just going to be negative 2790.679 joules. So that's basically the answer for work done. But our work is not done. And the reason why our work is not done is because it's just simply not done. And the reason why is because we have to put our work in the proper number of significant figures. And if you look back at what we used, we see that what we solved, the lowest number of significant figures for the values used is 3. So meaning like 1.00 mole, 3 sig figs, 298 Kelvin, 3 sig figs. So we have to put our answer in 3 sig figs. So work done is going to be approximately negative 2.79 times 10 raised to the power of 3 joules, or negative 2.79 kilojoules. So that is basically the answer to this part of the question. And our work is still not done because guess what? We're also told to find the change in internal energy, right? If you go back to the question, we're also told to change in internal energy, please. Yeah, that's it. So the change in internal energy is just simply what we know, the adiabatic work done plus heat during an adiabatic process, right? So I'm saying like the change in internal energy for an adiabatic process is just simply this. But the good thing about this is that in an adiabatic process, there is no heat transfer from the system to the surroundings and vice versa, because this is a system where there is no heat transfer whatsoever. So in an adiabatic process, Q is always going to equal 0. So hence, the change in internal energy in an adiabatic process is the same thing as work done in an adiabatic process. So this is it. So whatever the value for work done is the same value for the change in internal energy in an adiabatic process. So changing U for adiabatic is just simply going to be negative 2.79 times 10 to the power of 3 joules, or negative 2.79 kilojoules. So basically, this is the change in internal energy for an adiabatic process. So yeah, that's it. That's basically all we have to do to solve this question. If you have any questions, please put it in the comment section. That is why I'm here, to help you. And if you have any concerns or suggestions to grow this channel, or anything you want to suggest, please also put in comment section. I'm also here to help you guys. That's the whole point of making these videos, for all of us to learn. I also wanted to mention that if you're a student who is struggling in any of your STEM related courses, whether you're in middle school, high school, or college, I'm a tutor that helps students succeed in all their STEM related courses, as well as assist them in navigating their academic life. So if you're trying to improve and succeed, I am the tutor for you. Make sure you email me at shahabitutoring@gmail.com for you to start succeeding today. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.